everyone. Today we will be presenting on zero-shot multi-speaker text-to-speech with state-of-the-art neural speaker embeddings. So here's a quick overview of the talk. First, we'll show some background on multi-speaker TTS, neural speaker embeddings, such as the learnable dictionary encoding method. Then we'll show how we can incorporate speaker embeddings into tacotron-based TTS, as well as experiments on zero-shot speaker similarity. And we'll also show some results of a large-scale listening test to demonstrate the effectiveness of this approach for modeling unseen speakers. So here's an overview of our end-to-end TTS. So we are using a tacotron and vocoder type setup. So tacotron learns mappings from characters or phonemes to a mouse spectrogram. We are using phoneme input, and and then a vocoder converts the mouse spectrogram into waveforms. So different from a conventional TTS, which has separately trained modules, we have a sort of encoder-decoder model with attention that we train all together, and then we have a separate neural vocoder, which is WaveNet. So the goal of end-to-end multi-speaker TTS is to synthesize in the different voices of hundreds of different speakers with a single model, ideally without having to retrain the entire system, using a very small amount of target speaker data. And we'd also like to be able to generalize to unseen speakers who are not seen in the training data. So there's two types of approaches to multi-speaker TTS in the end-to-end setting. The first one is model fine-tuning. So this is where you take some data for your target speaker, a small amount, it can only be maybe just a few minutes, and you use that data to retrain the model a little bit. This works well even if you only have a small amount of data, but this data has to be basically TTS quality data that's, high quality recording conditions with transcripts. And of course, you have to retrain the model additionally for every new speaker. So a different approach is transfer learning from ASV, which is automatic speaker verification. So in this approach, you require even less target speaker data. It can work well with just a few seconds. Transcribed data is not required. The adaptation data can be low quality, doesn't have to be TTS level of high quality recording conditions. And so basically, you use a separately trained ASV system, and the system can be trained on thousands and thousands of speakers, so you can get a really nice representation of the speaker space that's separate. And then no additional training steps for TTS are required for new speakers. However, we have found, and also other researchers have found, that speaker similarity for unseen speakers is not as good as speaker similarity for speakers who are seen in the training data. So here's an illustration of the approach. So we pre-train a speaker recognition model to get speaker embeddings. Then we input speaker embeddings to TTS. So the speaker encoder is totally separately trained. And during inference, target speakers don't have to be seen during training. We can do this in a zero-shot manner by just getting the speaker embedding using a little bit of the target speaker's speech and just inputting that into the TTS model along with the text. So our TTS architecture is basically tacotron 2 with dual source attention. So here is our encoder, and it's similar to tacotron 2, but it's a little different. Instead of a CNN-based encoder, we use CBH plus LSTM. We also use, our encoder has self-attention as well as forward attention, and our decoder also uses dual source attention to combine these two outputs. And we have a postnet, which does spectral shaping and enhancement, and the output is a mouse spectrogram, and then we use a WaveNet to convert into a waveform. And so what's new in our architecture here is the speaker embeddings. So we try inputting speaker embeddings at 3 different locations. The first one is to concatenate with the outputs of the encoder and input it to the attention. The second one is to input to the prenet, and the third one is to input to the postnet. So we try some preliminary experiments because we have some questions about what is the best input location and what is the best training strategy. So for input location, we try input to the prenet, input to the attention, both prenet and attention, and all three of prenet, attention, and postnet. For training strategy, we want to see, should we train from scratch or should we pre-train the model somehow? And also, do we want to train in a gender independent manner where we use all the data together, or train gender dependent models using male and female data separately? And so in these sort of preliminary experiments, we do an objective evaluation. We're looking at speaker similarity objectively between the original voices and the synthetic speech using cosine similarity. And in particular, we're interested in similarity of unseen speakers. So the data that we're using in these experiments are the VCTK corpus. So this is 109 English speakers who have different English dialects. So first of all, from scratch training versus warm start. Training from scratch means we train on VCTK data only. And we found that it took about 4 days to get model convergence and to get reasonable quality and speaker similarity. Warm start training means we initialize our multi-speaker model using parameters from a well-trained single speaker model. We use the Blizzard 2011 Nancy data, which incidentally has a 3 times larger vocabulary. And we found that this only took 1 day of additional training with VCTK to get similar quality. So this let us iterate experiments much more quickly. So we decided to use warm start training. For additional results, we look at gender dependent versus independent and also input location. So the metric we're using here is cosine similarity, which ranges from -1 to 1. And higher values mean more similar. So the things we're comparing with this similarity are we extract X vectors from the original speech, and then we extract X vector from the synthesized speech of the same speaker, the same target speaker, and then we measure similarity. So we want the synthetic speech to be as similar as possible to the original speech. And in particular, we're interested in unseen speakers. So if you look at the dev set speakers, which are totally separate speakers from the training set, we find that the best speaker similarity for these unseen speakers are if we do gender dependent training and prenet and attention as the input location for the speaker embedding. So now I will turn it over to Jeff, who will talk about our neural speaker embeddings.
Now we move on and ask the following question: what kind of speaker embeddings for our multi-speaker TTS setup produce the best synthesis? Typically, in an end-to-end speaker recognition model, there are 3 components: an encoder network, a pooling layer, and a classifier. An encoder transforms the input features to frame-level representation, which is typically of variable length. The pooling layer pulls across these variable length frame-level representations and generate a fixed-size utterance-level representation. This utterance-level representation is later used for PODA for speaker verification, and it is the embeddings we extracted for our multi-speaker tachytron. Lastly, the classifier classifies the embeddings with different objective functions. Various work has proposed different improvements for each of these components. For example, TDNN and ResNets are a typical choice for the encoder network. Statistical pooling and the more recently introduced learnable dictionary encoding are 2 examples of the pooling layer. Cross entropy and angular softmax losses are 2 of the objectives to train the speaker recognition model end-to-end. Now let us look at these components more closely as described in our paper. For more detailed studies of these components, we encourage you to read the reference paper below. The conjunction of a TDNN, statistical pooling, and cross entropy loss produce AX vectors. The conjunction of the ResNets, the learnable dictionary encoding layer, and the angular softmax loss produce the LDEs. Here we explain what the learnable dictionary encoding method is. This method summarizes the frame level representation X to a fixed size embedding by mapping these X to a dictionary with a predetermined number of clusters. Each frame X is self-assigned to this cluster by computing the Euclidean distance. And we do this for every frame. Then these clusters are aggregated to form the embedding. So we can do this for just the mean factors, or we can do these for both mean and standard deviation factors. To gauge the effectiveness of these embeddings, we perform speaker verification experiment. We train these embeddings on FoxLab 1 and 2, which is extracted from YouTube videos with over 7,000 speakers. Our baselines are I vectors and X vectors. We examine the hyperparameters of the LDE embeddings, where we vary the speaker embedding dimension, the training objective, the pooling method, and whether post-processing is applied or not. And we ended up with 17 total embeddings and systems. This is the results of our speaker verification experiment. The first column is our speaker embedding. The second column is the embedding dimension. The third column is a pooling method of either mean or both mean and standard deviation vectors are pooled. The fourth column is the objectives for model training. The fifth column is post-processing, whether post-processing is applied or not. The last two columns are the objective measure for speaker verification. And the lower these numbers are, the better the systems are. We can see here that LDE3 achieved the best speaker verification results. And generally, LDE has better number than our baselines. We want to emphasize here that these numbers were only state-of-the-art a year ago, and there were many more where it came out afterward. For readers that are interested, you can refer to the reference paper below. Now, what previous work lacks is a systematic experiment on comparing and evaluating the effectiveness of different speaker embeddings for multi-speaker TTS, which we present here in our experimental setup. We have 3 experiments. The first is the vocoded speech, where the ground truth spectrograms are used as input to the vocoder. Secondly, we have the X vectors for our multi-speaker TTS. Lastly, we employ LDE for our multi-speaker TTS setup. We conducted a large-scale listening test, and participants rate the synthesized voices by their naturalness from 1 to 5, and speaker similarity from 1 to 4. This is the results of the listening test. The first column is our baseline and the speaker embeddings used in our TTS setup. The second and third column is the naturalness and speaker similarity scores. We want you to focus on the test column. Our experiment is conducted in the zero-shot fashion, such that the input text and speakers are totally unseen during training. We want to emphasize that the train, depth, and test splits has separate speaker sets. Some observation. We can, in general, the LDE embeddings achieve better results in terms of naturalness and speaker similarity compared to the baseline X vectors. We can also see from the table that LDE3 achieved the highest synthesized quality in terms of naturalness and speaker similarity, which is consistent with our speaker verification experiment. Another observation is that there is no drop in terms of naturalness from training to test. However, there is a drop in terms of speaker similarity comparing training and tests, and this exemplifies the difficulty of maintaining speaker similarity in a multi-speaker tachytron. We also encourage you to listen to the samples in the URL link here. In this work, we empirically examine several factors for multi-speaker TTS such that the synthesized voices have higher speaker similarity in the zero-shot condition. We observed that warm start training can produce equally well samples while requiring much less time to train. Gender-dependent training produces better speaker similarity than gender-independent training. Speaker embeddings input to prenet and decoder attention produces the best results. Furthermore, LDE embeddings achieve better speaker verification and synthesize results. Thank you for listening, and if you have any questions, feel free to email Erica and I.